You ever stop and think what's actually going on inside your computer when you click something? It feels like magic, right? But it's not. It's this incredibly cool logical process. So today, we're going to pull back that curtain. We're going to deconstruct the digital brain and see exactly how it works by following just one single command. Ready? Let's get into it.
So, here's the game plan. We'll start big picture with the basic blueprint of a computer. Then we're going to zoom right into its brain, the CPU. After that, we'll talk about memory, and then we'll follow an instruction on its incredible journey. We'll even look at 2 different design philosophies and see how this all scales up to power, well, everything we use.
Okay, so first things first, let's talk about the computer's core blueprint. And I want you to just forget that whole magic box idea for a second, because really, at its core, every single computer out there, I'm talking from a massive supercomputer all the way down to the tiny chip in your smart toaster, it all follows the same basic plan. I know it seems super complex, but when you boil it all down, a computer is really just 3 main parts. You've got a processor, that's what does the thinking. You've got memory to hold all the information. And you have input/output units so it can talk to us. You know, your keyboard, your mouse, your screen. That's it. That's the blueprint for literally everything. And get this, everything a computer does. I mean, everything. From rendering a wild 3D video game to just adding up numbers in a spreadsheet. It all comes down to this simple 3-step dance. It takes something in, that's input. It does some work on it, that's process. And it gives you a result, that's output. Input, process, output. It's so simple, right? But it's also what makes everything possible. So we've got that basic loop down. Input, process, output. Now, let's zoom in on what is arguably the most important part of that whole thing, the process step. We're going to dive right into the brain of the whole operation, the central processing unit, or as you probably know it, the CPU. This is where the magic really happens. Yeah, the CPU is the absolute engine of the entire system. Think about it. Every single instruction from every single program you run has to go through the CPU to get done. It's like the master conductor of this huge, complicated orchestra, making sure every little part does its job at the exact right moment. But here's the thing. The CPU isn't just one big blob doing all the work. Nope. It's actually a team of super specialized parts, all working together perfectly. And we're about to meet the 3 stars of the show: the control unit, the arithmetic logic unit, and the registers. Each one has a really specific and really important job. All right, first up, we've got the control unit, or CU for short. The best way to think about the CU is as the project manager, or maybe a traffic cop. It doesn't do any of the math itself. Its job is to read the instructions from the program and then tell everyone else what to do. It points at the memory, at the ALU, and says, "You, do this now." It's the boss, keeping the whole operation running smoothly.
Okay, so if the control unit is the manager, then the arithmetic logic unit, the ALU, is the genius calculator on the team. This is the workhorse. Anytime a program needs to do, well, anything with numbers, add them, subtract them, compare them, the control unit sends that job straight to the ALU. The ALU is the part that actually crunches all the numbers.
And that brings us to our third team member, registers. Now, if the ALU is the calculator, think of registers as its own personal little scratch pad. They're these tiny, super-duper fast storage spots right there on the CPU chip itself. They hold the exact numbers the ALU is about to work on, or the answer it just figured out. The countertop analogy is perfect. It's way faster to grab something from the counter than to walk all the way over to the fridge, right? Same idea here. So, those super fast registers, they're actually just one part of a much bigger memory system. See, a computer is smart. It uses different kinds of memory for different tasks. It's all about creating this hierarchy, balancing speed against size and cost. It's definitely not just one giant bucket where everything gets thrown. Okay, let's talk about the 2 big ones you always hear about, RAM and ROM. Let's break it down. RAM, that's random access memory, is like your desk. It's your current workspace. It's fast, you can put stuff on it, move it around, but when you turn off the lights and go home, turn off the power, your desk gets cleared. It's temporary. Then you've got ROM, read-only memory. This is more like a printed book, like the computer's startup manual. That information is permanent. It doesn't vanish when you turn the power off, which is super important because that's where the basic startup instructions live. This chart really lays it all out, doesn't it? You can see RAM is volatile. That's just a fancy word for it forgets when the power goes out. ROM is non-volatile, meaning it remembers. And then you have flash memory, which is probably what's in your phone or that USB stick. It's kind of the best of both worlds. It's non-volatile, so it remembers everything, but you can still write new stuff to it. The main thing to get here is that each of these has a specific job, and that's why a computer needs all of them. All right, so we've met the whole crew, right? We have the control unit as our manager, the ALU as our math whiz, and all the different kinds of memory. So now, let's put it all together. Let's actually watch them work. We're going to follow one single command from start to finish and see this incredible high-speed dance in action.
This right here, this is the heartbeat of the computer. It's called the instruction cycle. It's a constant 4-step rhythm. Step 1, fetch. The control unit grabs the next instruction from memory. Step 2, decode. It looks at the instruction and figures out what to do. Is it addition? Something else? Step 3, read operands. It grabs the data it needs to do the job. And finally, step 4, execute. It hands everything over to the ALU to do the actual work. Fetch, decode, read, execute. And remember, this cycle is happening billions of times every single second. Mind-blowing, right?
Okay, so that fetch, decode, execute cycle is pretty much universal. But, and this is a big but, there are two different schools of thought on how to build the connections between the CPU and the memory. It really all boils down to one question. How do you set up the roads for instructions and data to travel on? Let's stick with that highway analogy. On one side, you've got the von Neumann architecture. This is what's in most of our computers. Think of it as having one big single-lane highway for everything. Both the instructions, which are like the driving directions, and the data, which is the cargo. It works, it's simple, but you can get a traffic jam. That's what we call the von Neumann bottleneck. Now, on the other side, you have the Harvard architecture. This one is smarter. It builds two separate highways, one just for the directions and another one just for the cargo. This means the CPU can be grabbing the next set of directions while it's still working on the cargo from the last trip. It's a huge potential speed up. So we have this amazing core process, this fundamental blueprint. But that still leaves a question, right? How do we go from that basic concept to the absolute powerhouses we have in our pockets and on our desks today? Well, the answer is scaling. You don't just make one brain work faster, you give it more brains to work with. And that's exactly what a multi-core processor is. When you hear that word core, just think of it as a complete, independent CPU. It's got its own control unit, its own ALU, its own registers, the whole shebang. So when you hear quad-core processor, it doesn't mean one brain working 4 times as fast. No way. It means you literally have 4 separate brains on one chip, all working together, all running their own instruction cycles at the same time. It's teamwork on a microscopic scale. And honestly, that is the most incredible part of this whole story. Our entire digital world, everything from the phone in your hand to the giant servers that power the internet, it's all built on this one simple idea. That fetch, decode, execute cycle we talked about, just repeated over and over and over, at speeds we can barely comprehend across multiple cores all at once. It's just staggering when you think about it. So, next time you tap your phone screen or click your mouse, take a second and just picture it. That elegant, lightning-fast dance happening under the hood. A simple, repeating rhythm that started decades ago and has grown to power, well, everything. It makes you wonder, doesn't it? If this cycle built our world today, what worlds will it build for us tomorrow?